Hi, this is Miss Logan. Today I'll be talking about momentum and a little bit about the conservation of momentum in collisions. Let's first talk about how we define linear momentum. So by linear, we mean that we're traveling in a straight line. Okay? So for linear, we use P. Now this arrow here represents that this is a vector. So it has to have direction and it can be negative or positive. We are starting to get to the point where we're kind of running out of variables, so this is when you really need to memorize that P equals momentum. So P equals mass in kilograms times velocity, which is in meters per second. So how we get the vector portion is from this velocity here. Our unit is kilogram meters per second. Why do we have that? Well, we have mass times velocity, which is kilograms times meters over seconds. All right, so let's relate momentum and Newton's second law. You may notice that they look very similar. The only difference between them is the acceleration and the velocity. So this is Newton's second law. The sum of the forces equals mass times acceleration. Now, let's think about this. My total force is equal to mass times acceleration. We can also write acceleration as velocity over time. Now, as you look back at your notes from momentum that you just took, mass times velocity equals momentum. So the sum of the forces equals the change in my momentum over time. So that's how we relate Newton's second law to momentum. Impulse is something that is related to both force and momentum. So I, which is also a vector, equals the force times the change in time. Okay? So as we have a smaller change in time, we also are going to have a smaller impulse. Once again, this is a vector, so it's going to have a direction. For our units, they're newtons times seconds. If we write that out, that's kilogram meters per seconds. This is the same unit as momentum. So these are actually the same thing. How cool. Now let's actually go over this derivation to see that they are the same. So previously, this is how we related Newton's second law to momentum. And I did that derivation a little bit earlier in this lesson. Now, if I move this t, delta t, to the other side, I'm going to rewrite it like this. Force times delta t equals P. Now, we just saw that this also equals I for impulse. So therefore, the impulse is also the change in the momentum. So really, these three different things are all related, and my impulse and change in momentum are the same thing. So once again, my impulse is my force over delta t. So basically, if I have a large force and a small t, I will have a large impulse. Or I can have a small force over a long period of time and also get a large impulse. So this is a linear relationship, so either one can affect our impulse. Lastly, let's talk about the conservation of linear momentum. Now this lesson is going to go into our collisions lesson as well, but it's an important part. So the net force acting on an object is its change in momentum. And remember, we got this from Newton's second law. We already wrote this down. So if the net force is 0, the momentum isn't changing. So my conservation of momentum says all of my momentum before equals all my momentum after. Now, how is this going to affect what we're doing? The internal forces cannot change the momentum of the system. It has to be something going on outside of it. For instance, maybe something is crashing into each other, a piece is falling off, a gun is firing, so the mass is changing. So if I look at all the forces before, all my momentum before and all my momentum after, they're equal. Now, what does this mean? The momenta of a components may change. At the beginning, I might have mass 1 is going at velocity 1. I also have mass 2 is going at velocity 2. So that's my momentum 1 and my momentum 2. Now, after something happens, maybe they collide into each other, maybe they combine. So now I would have some velocity together, an N1 and M2. Now, this gets in a little bit more detail with collision, so we're really not going to worry about this. But this is telling me that these two things are equal because of some external force. Now, here's another example than the one I gave. So, for instance, we have these two boats, and maybe they both start at rest, okay? So my momentum before equals my momentum after. Now, if they're both at rest, that means that everything before is actually 0 in this situation. So that means 0 equals whatever happens after. So maybe I have M1 V1F plus M2 V2F. Now, given my masses and one of the velocities, I could actually figure out what their final velocities would be. And that'll get us into collisions, which will be our next flipped lesson in a few days.